In this video, I'm going to be talking about a few different things. First, I'm going to talk about how you can use something called the dot product to find the length of any vector in space. Then, I'm going to show you an example where the dot product doesn't work to find the length of a vector in space. Then I'm going to correct that example with something called the metric tensor, which allows me to find the length of any vector in any coordinate system. So first, I'm going to start with a basis, and I'm going to make two basis vectors. I'm going to have E1, and it's going to be equal to 1, 0. And I'm going to have a second basis vector called E2, and that is going to be 0, 1. Now, what do these basis vectors look like? Well, if I were to draw them out, E1 has an x length of 1 and a y length of 0. So it's just going to look like this. This is going to be the x and y axis, by the way. X and y. And then E2 is basically going to be the opposite. It's going to be 0 in the x direction and 1 in the y direction. So it's going to look like this. Now, what is a basis vector? Well, it means that for any vector in two-dimensional space, I can express it as a sum of two components, each multiplied with one of these basis vectors. For example, let's say I have the vector 2, 4. I can express this as 2e1 plus 4e2. And just to check that, I can plug it in. I can plug in my basis vectors like so. And obviously, the 0 terms go away, and I just have 2, 0 plus 0, 4, which equals 2, 2, 4, which is what I got there. So what the dot product is it takes two vectors. Now, I'm just going to do a quick definition here. I'm going to say one vector has components 1, 1, and another vector, and we'll call this A. And another vector B has components, we'll use the same one that we just used, 2, 4. What is the dot product? Well, how we do it is we basically just multiply out the x components with each other and the y components with each other, and then we add them up. So how you'd represent that is you have A, you have dot, you have B. That means we're taking the dot product. That's what that symbol is. And it's basically multiply these together. So you have 1 times 2, and then you add that with these two multiplied together, 1 times 4, and you would get 2 plus 4, which is equal to 6. And that is the dot product of these two vectors. Now, the dot product does have a physical significance, but for now, I'm really just going to talk specifically about doing the operation and writing it as, the x components multiplied together with the y components multiplied together. Because what we're going to use it for is, let's say I want to find the length of a vector. Let's say vector v, we're going to call it 3, 4. Normally, and I'll draw it out, you draw it out like this. Has a length of 3 and a height of 4. To find the length, normally, you use the Pythagorean theorem. X squared plus y squared equals r squared, and we're trying to find the length r. And our x is obviously 3, and our y is 4. And we have 3 squared plus 4 squared equals r squared, and 3 squared. And I'm sure you would know this from something like high school geometry. 3 squared is 9, plus 4 squared is 16. 9 plus 16 is 25, and you square root that, and you get 5, so our length is 5. That should be pretty clear. But, that's how you'd find the length of a vector like this. You'd use the Pythagorean theorem. Now, we can express the Pythagorean theorem and the vector length in terms of a dot product. And earlier we said we had a vector A, which was, let's give it components A1 and A2. And actually we'll do this because this is easier, AX and AY. And then we have a vector B with components BX and BY. The dot product of those, we said, and I'm just restating this because it's important, is AX BX plus AY BY. But what if A and B were the same? Let's just take A dotted with itself, A dot A. We would get AX times A sub X, which is AX squared, and we get AY times AY, which is just AY squared. And this should look familiar. That means if we have some vector with components AX and AY, this dot product, if we have some length R, is just equal to R squared. And so for any vector, we can say that its magnitude, I'm going to use this way of representing magnitude, is squared is equal to the vector dotted with itself. And what that is saying is that it's just the Pythagorean theorem. Now, I'm going to show a scenario where this doesn't work. Let's say I have a new basis. So I'm not using my 1, 0, 0, 1 regular, 1 unit in the x direction, 1 unit in the y direction basis vectors. I'm not using those anymore. I'm going to create a new basis. I'm going to E bar 1, I'm going to call it instead of E1 because we already used E1. I'm going to say that vector is equal to 1, 0. So it's going to be the same as E1. But I'm going to do a new second basis vector. I'm going to call it E bar 2. And let's make it 2, 1. What do these basis vectors look like if you draw them out? Well, E1 is still the same. Let me make that straighter. 1, 0. But E2 is different now. It's at 2, 1. And so 1, 2, 1. This is our second basis vector. E2, and this is at 2, 1. Now, if we want to find the length of a vector expressed with these bases. So earlier I obviously talked about you have your vector, and I'll actually write it out here. You can define your vector, V, with a component Vx times E1 plus Vy times E2. Now we have a different basis. So let's say I have, and I'll do an easy vector here. Let's do just the vector 2, 1. How could we express the vector 2, 1? Well, we could say it's, and we'll call this vector t, lowercase t. We're going to say that t is equal to 0 times E1 plus 1 times E2. And let's try and find the length of it using the dot product. So our dot product now, we take the components, we say our length of t squared is equal to the dot product with itself, so it's going to be 0 squared plus 1 squared, and that's just equal to 1. And if we take the square root of 1, it's just going to be 1. So our length of t is 1. But that's obviously not true, right? I mean, think about it. If we draw out this vector again, 2, 1, you know, the length is obviously not 1. If the length was 1, the vector would have to lie somewhere, and obviously this isn't to scale, but it would have to lie on the unit circle, which has a radius of 1. And, you know, obviously it doesn't. I mean, if you move 2 to the right, you're already outside the unit circle. You can't get back in by adding any type of y component. So that obviously doesn't work for this. So how do we fix that? Well, we introduce something called the metric tensor. Earlier, I said that the length of a vector v, and I'll write out what v is again. I said that the length of this vector was vx squared plus vy squared. And that is technically true, only if the two basis vectors e1 and e2 are orthogonal. What does that mean? That means that e1 dot e2 equals 0. Because what is e1 dot e2, right? It's equal to e1, the length of it, times the length of e2 times the cosine of the angle between them. Because what the dot product actually has to do with is basically how much of a vector is parallel to another vector, and you're multiplying the components that are parallel to each other on the same line. You're multiplying those together. That's for another video. But you just have to know that this only works in this specific case where e1 and e2, the dot product of them is 0. Obviously, it didn't work with the other case because we had e1 bar dot e2 bar is equal to, I can't remember what I made it. It was 1, 0 dotted with 2, 1. And obviously you have 1 times 2, which is 2, plus 0 times 1 is 0, is 2. That's not equal to 0. So this definition doesn't work. So what definition does? How do we find the length of any vector, regardless of if the bases are orthogonal or not? If these two aren't orthogonal, how do we find the length? We can't use the dot product anymore. We have to use something else. And this is where the metric tensor comes in. We can actually manipulate this a little bit. We can say that, I'm going to do a little bit of algebra here. We could say that the length of v, or v dot v, we're going to call this v squared. And you know, that makes sense. It's v times v. And so yeah, of course that's v squared. And then you could say that the length of v then, which is normally the square root of the dot product, is just the square root of v squared. You know, that makes sense. If you have the square root of something squared, you get that same thing back. But you can't take the square root of a vector, so obviously what do you get back if you square the vector and then take the square root? You get a scalar. What is that scalar? That scalar is the length of the vector. So I'm going to square this right here. I'm going to say that the length of v squared is equal to v squared. And I get vx e1 plus vy e2 squared. And now this is where the algebra comes in. You just have to multiply this out. And what you'll end up getting is vx squared e1 dot e1, which is just 1, because obviously any vector dotted with itself is, actually, I'm sorry, it's not 1. You get vx e1 dot e1. Forget what I just said. And you get a term that is vx, vy, you have e1 dot e2, plus a term where you get vy, vx, e2 dot e1, and then you get a term that's vy squared, e2 dot e2. Now, normally, normally and this proves why your vectors need to be orthogonal for the regular one to work. If your two vectors are orthogonal, that means e1.e2 is 0. And so these terms normally would vanish, and you would have vx squared times e1 dot itself plus vy squared, and you'd have e2 dot itself. But, it's Pythagorean theorem, vx squared plus vy squared. But when they're not orthogonal, these terms don't go away. And so what we're going to do is we're going to make a matrix. And we're going to call this matrix Gij. Ij are just indices referring to different rows and columns of the matrix. Now, we're going to call this E1.E1. That's our first row and our first column. Our first row and our second column we're going to say is E1.E2. And then we're going to do E2.E1 for our second row and our first column. And then for our second row and column, we're going to do E2.E2. And so you can actually rewrite this formula. You're going to say Gij is equal to E sub I dotted with E sub j. Because, when we expanded it out, we got all those terms that were like E1, E2, E1, E1, E2, E1, and E2, E2. We got all those terms. And we're collecting that into a matrix. So now I'm going to rewrite this a little bit. And I actually just had the formula written out, and I'll write it out again. You had vx squared e1 dotted with e1. And we're going to rewrite this now. Instead of e1.e1, we're going to say g11. And we had 2 times vx, vy, g. Now, these two are going to be the same. Why is that? The dot product is commutative, which means that you can flip it around and it would still be the same either way. It's the same thing if you have, let's say, 2 times 1 or 1 times 2, they're both going to be the same value. And so you can just call this G12 or you can call this G21. It doesn't really matter, but they're the same. And so instead of saying Vx, Vy, G12 plus Vx, Vy, G21, you can just have 2 times Vx, Vy, and then whichever one you want to put, 1, 2, or 2, 1. It doesn't really matter. They're the same value. These two are the same. And then you have your third term, which, and I'll write it down here, is Vy squared G22. And this is actually the formula right here. This is the length squared. And so if you wanted to find the length of a vector, you would just take the square root of this whole value right here, and you get your length. But we're going to go a step further, and we're going to do a little bit of a notation change. I've been calling these components Vx and Vy, but I'm going to shift, and I'm actually going to call them something else. I'm going to call them V1 and V2. This does not mean V to the first power or V squared. That's not what those mean. That just means that they're contravariant vectors. Now, what does that mean? That means, well, if you have a grid and each square has a area of 1, so your 1 by 1 regular unit grid, and you have a vector, right? Its components, let's say 2, 2. If you were to do some sort of transformation of the plane and change this grid, let's say we dilate this grid by 2, right? We have this original vector that was 2, 2. But now we've doubled it. We've doubled the size of the grid. And so the grid looks more like this. This is our new unit vectors, this and this. This is E1 bar and E2 bar. What's happened is originally we had our vector that was 2, 2 in our original basis. But what we've done now is, since we've made the coordinate grid bigger, the actual components of the vector get smaller in the new reference frame. In this new frame, since the unit square has an area of 4, or 2 times 2, this is actually now the vector 1, 1. So that's why we call this a contravariant component. What that means is when we multiply our grid by some scale factor, it divides that component by the scale factor. We multiplied the grid by 2, and our components were divided by 2. They went from 2, 2 to 1, 1. So that's why we call this contravariant components, is because it contradicts what the transformation does. I'm actually going to throw in a new vocabulary word as well. E1 and E2, the basis, are both covariant vectors. They're co, or with the grid. So when you multiply the grid by 2, that means the basis vectors grow by 2. And what that actually gives rise to, I mean, if you think about it, if you multiply this by 2 and this by 2, but then you divide this by 2 and you divide this by 2, this all cancels out. And your vector length will be the same or invariant. It doesn't vary from coordinate system to coordinate system. If you have a vector v with some length, that length isn't going to change no matter what coordinate system you go to. It's always going to have the same length. Anyways, I've introduced this new change in notation. I'm going to wrap it up with this. Earlier, I said that our length of the vector squared was v1 squared times e1 dot e1 plus v1 v2 e1 dot e2, and this is obviously g11 and g12 or g21, whichever one you want to use, plus v2 squared e2 dot e2. This is, of course, g22. We can actually compact this into a summation formula, which is, think about it right here, we have v1 times v1 and e1 times e1, and then we have v1 times v2 times e1 times e2, and so you have this pattern 1, 1, 1, 2, 2, 1, and these are obviously the same, so there's actually 2 of them, my bad, I forgot to put that, and 2, 2. And so you could call this the sum over mu, or actually I'm going to use ij, sum over ij of v times I, v, not times I, v superscript I, and v superscript j times g ij. And this might look really confusing. And basically what these indices mean is you're just summing over each of these. And so you'll get a term where I is 1 and j is 1, and that would be this first term. You get a term where I is 1, j is 2, and you get one of these, or I is 2 and j is 1, you get another one of these in the middle, and then both of these are 2, you get this final term here. That's just what this summation means. And that is the length of the vector squared. And this is actually a more general definition for the dot product that allows you to calculate length for any vector in any coordinate system, regardless if the bases are orthogonal or not. And so, in conclusion, you are left with this formula for the dot product. If your basis vectors are orthogonal, which means they're at 90 degrees to each other, then your dot product is just the square root of your vector dotted with itself. However, if E1 and E2 are not equal to 0, let's say you have a different one. In this case, theta is less than 90 degrees. Then this does not work. Instead, your length is equal to the square root of sum ij times vi vj g sub ij. And so this is the more general formula. As always, if you have any questions, feel free to ask them in the comments. Thank you very much for watching.